Good afternoon to all of you. First of all, I want to introduce myself. Myself Ankit Acharya, working as an assistant professor in mathematics in Hasmukh Goswami College of Engineering. So today my topic is linear transformations, and let's see today's my content: inverse linear transformations, matrices of general linear transformations, and isomorphism. So before we start today's content, we have to understand some basic topics, some basic content related to this content. So last time I already discussed all these topics, so just briefly we see some important topics which is related to this topic. Last time I defined kernel of T and range of T. What is kernel of T? That is, we have to collect all the vectors from the domain such that images of that vector is equal to the 0 vector, right? So that is the set of all that vector whose image is equal to 0 vector is the kernel of T. Range of T is actually the images, collect all the images from the codomain is actually the range of T. And we see some important theorem, that kernel of T is a subspace of V and range of T is a subspace of W. V is a domain and W is a codomain. So here is a proof which already we last time see. Here some simple example that we have to find the kernel of T and range of T in zero transformations, identity operator and rotation, right? And we already seen some example last time, right? So some simple example. Next is rank of T and nullity of T. Now what is rank of T? That is dimension of range of T is called rank of T, and nullity of T is actually the dimension of kernel of T. And after that we see important theorem which we use in some examples. So what is theorem says, that if T from Rn to Rm, so standard matrix for T is of course M cross N matrix, right? So nullity of T is exactly the nullity of that standard matrix, and rank of T is exactly the rank of that standard matrix. Here is the rank nullity theorem, which is also called dimension theorem for linear transformation, which is very important, that if T from V to W is a linear transformation, then an n dimensional vector space V to vector space W, then rank of T plus nullity of T is equal to the dimension of the domain. Okay, so is actually rank nullity theorem. After that we see some example. To solve this example, we have to find actually the basis and dimension of kernel of T and range of T, and then verify dimension theorem, right? So to find basis for kernel of T, we actually find the null space of that standard matrix. We find null space of that standard matrix, and what is rank of T is actually the rank of this standard matrix, which is number of non-zero row in this row echelon form matrix of this matrix, right? So after that, okay, this is also one good example with the same question. We have to find range of T, kernel of T, and rank and nullity of T, right? We see all this thing last time. After that we see 1-1 linear transformation. Okay, so 1-1 linear transformation, how we define? If T of U is equal to T of V, then U is equal to V, then must be U is equal to V if T is 1-1 linear transformation. Okay, and to become 1-1 linear transformation, these three statements are equivalent. So we use this three statement in some example to solve some example, that T is 1-1 if and only if kernel of T is equal to the singleton theta, that means theta is a 0 vector, nullity of T is equal to 0. Okay, so if we prove that nullity of the transformation is 0, then T is 1-1. Okay, so that thing you have to remember. So to become 1-1ness, we have to prove that nullity of that transformation is equal to 0. So here is a proof of that theorem. Okay, here is example: T from R6 to R4, which is multiplication by the matrix. So this matrix is actually the standard matrix for the given transformation, 4 cross 6. Okay, and we have to check that the given transformation is 1-1 or not. So we have to convert this matrix into row echelon form, and in row echelon form only two non-zero rows in this matrix. Okay, so nullity is 4, because dimension of the domain is actually 6 and rank of T is equal to 2. So using the rank nullity theorem we can find easily nullity is actually 6 minus 2, so 4. Okay, so nullity is 4, so clearly the given transformation is not 1 1. Okay, because 1 1ness the nullity should be 0. Here is the another theorem which is actually the same theorem, but this is the operator, right? T from V to V, linear operator. Then these 4 statements are equivalent. Just one statement is add, that range of T is actually range of T is equal to hold the vector space V. Here is the proof. And now this thing we already see last time. Okay, so today our first content is inverse linear transformation. So how we make inverse linear transformation? Let's see. T from V to W is a linear transformation. Then the range of T, which is denoted by range of T with this notation, is actually the subspace of W that we know, consisting of all images under T of vectors in V. Now if T is 1 1, then each vector W in range of T is the image of a unique vector V in vector space V. Okay, because see, T is 1 1, right? So one vector has only one image. In fact, any two distinct vector in the domain have a distinct images. Any two distinct vector in domain have a distinct images. And to become a function that we know, that every vector in domain has a unique value in codomain, right? Has a unique image in codomain. Okay, so if T is not 1 1, in that case we cannot define from the codomain to domain function, right? We cannot define a function from codomain to domain. So 1 1ness is very useful here, right, to become a inverse linear transformation, to become a function. So this uniqueness allows us to define a new function called the inverse of T, and is denoted by T inverse, that maps W back into V, that maps W back into V. The T inverse defined from range of T to domain V is also a linear transformation. Okay, and one note here, that standard matrix for T inverse is exactly the inverse of standard matrix of T. We will use this note in some example. Okay, so just mind it that standard matrix for T inverse is exactly the inverse of standard matrix of T if T is invertible. So let's solve some example. First example, T from R3 to R3 with the linear operator defined by the formula T of x1, x2, x3 is equal to 3x1 plus x2 minus first coordinate is 3x1 plus x2, second coordinate is minus 2x1 minus 4x2 plus 3x3, third coordinate is 5x1 plus 4x2 minus 2x3. Now we have to determine whether T is 1 1. If so, find T inverse x1, x2, x3. So here is the standard matrix. How we make this standard matrix? We have to take first coordinate. What is first coordinate? 3x1 plus x2, and in first coordinate the coefficient of x1, x2, x3 is actually the 3 1 0. So that is our first row of the standard matrix, right? To become second row, we have to take second coordinate, that is minus 4x1 plus 3x3 minus 2x1 minus 4x2 plus 3x3. So in second coordinate, what is the coefficient of x1, x2, x3 is minus 2 minus 4 3. Okay, so the second row is minus 2 minus 4 3. And what is the third coordinate? 5x1 plus 4x2 minus 2x3. And to become a third row, we have to take coefficients of x1, x2, x3, that is 5 4 minus 2. Okay, so this is our standard matrix. Now first of all we have to check that the given transformation is 1 1 or not, right? So what we have to do, we have to check that this matrix, first of all we convert this matrix into row echelon form, and let's see in row echelon form how many non-zero rows. In row echelon form, how many non-zero rows? Whatever the non-zero row in row echelon form, that is our rank, and from rank we can easily find the nullity, and if nullity is equal to 0, then we can say that T is a 1-1 linear transformation, right? So let's first we convert this standard matrix into row echelon form. So here is our first process. We have to multiply in this matrix. You can see we have to multiply first row by 2 by 3 and add into second row, and first row by minus 5 by 3 and add into third row. So this minus 2 and minus 5 become 0 in this matrix, right? So that is our first process. We have to multiply first row with 2 by 3 and add into second row, and we have to multiply first row with minus 5 by 3 and add into third row. So you can see we will get this matrix 3 1 0 0 minus 10 by 3 3 and 0 7 by 3 minus 2. Now in first row, what is our leading entry? 3. Below the leading entry we make already 0, right? Now in second row, what is our leading entry? Minus 10 by 3. So first of all we have to make this leading entry become 1 or minus 1, right? So we can easily below this leading entry becomes easily we can make 0. So let's try to make that leading entry which is in second row 1 or minus 1. So we have to multiply second row with 3 by 10. Okay, so the second row become 0, minus 1 and 9 by 10, right? And again third row we multiply with 3 by 7. So 0, third row becomes 0, 1 and minus 6 by 7. Okay, now below this leading entry, below that minus 1 we have to make 0. So just add second and third row. So we have to multiply second row with 1 and add into third row. So this is the last process. We multiply second row with 1 and add into third row. So this row echelon matrix become 3 1 0. First row is 3 1 0, second row is 0 minus 1 9 by 10, and third row is 0 0 3 by 70. So you can see all of 3 rows are non-zero rows. So clearly rank of T is equal to 3 and nullity of T is equal to 0. Why nullity of T is equal to 0? Because we know the rank nullity theorem. We know that rank plus nullity, rank of transformation plus nullity of transformation is equal to n, where n is actually the dimension of the domain. Okay, so here the dimension of R3 is equal to 3. So rank is 3. So clearly nullity is 0. And if see nullity is 0, so using that theorem we can say that T is 1 1. Okay. So now we can find T inverse x1 x2 x3, and we use that note that inverse, we know that inverse of standard matrix for T is exactly the standard matrix for T inverse. Okay, so let's see here determinant of T. First of all we have to find determinant of T from this matrix. You can see 3 into what is determinant of T? 3 into 8 minus 12 minus 1 into 4 minus 15. Okay, so this is our determinant. So 3 into 8 minus 12 minus 1 into 4 minus 15, that is minus 12 plus 11, that is equal to minus 1. Okay, also to find inverse linear transformation we have to find cofactor. Okay, we have to find cofactor of the given matrix, right? How we find this cofactor? I will explain. The first cofactor, what is our matrix actually? 3 1 0. Here is our matrix 3 1 0, minus 2, minus 4, 3 and 5, 4, minus 2. So first of all I want to find cofactor, that is called C11. Why this is C11? Because I want to find the cofactor of 3. I want to find cofactor of 3. Okay, so I want to find cofactor of this 3. So we have to remove the column, this column and this row. So minus 4, 3, 4, minus 2, this determinant and also we have to multiply with minus 1 raised to 1 plus 1. Why 1 plus 1? Because this element is actually in the first column and first row, so that's why 1 plus 1. Okay, and that's why we denote with this notation C11. So what is this one? Minus 1 raised to 1 plus 1, that is equal to 1, and minus 4 into minus 2, 8 minus 4 into 3, 12, so that is minus 4. Similarly, we can find cofactor of 1. We can find cofactor of 1. So that is minus 1 raised to 1 plus 2 into, remove this column and this row, so 4 elements remaining, that is minus 2, 3, 5, minus 2. Now minus 1 raised to 1 plus 2 is minus 1 raised to 3, so that is minus 1 into 4 minus 15. Okay, 4 minus 15, so minus 11 into minus 1, so 1, 11. Clear? So now you can find all the cofactors of all the elements, right? So now you can see on the screen, C11 is minus 4, C12 is 11. Similarly, we can find C13 is 12. Okay, so that is C21 is 2, C22 is minus 6, C23 is minus 7, C31 is 3, C32 is minus 9, C33 is equal to minus 10. Okay, so this subscripts, these two subscripts are denoted is actually the number of that element is in what row and what column. Okay, so now this all the cofactor we have to, using that all the cofactor we can find adjoint of the standard matrix, that is we have to put in column. So C11, the cofactor C11, C12, C13 we have to put in the column minus 4, 11, 12, 2 minus 6 minus 7, the column, first column is minus 4, 11, 12, second column is 2 minus 6 minus 7, and third column is 3 minus 9 minus 10.